All right. We're going to see if we can do this. Now, I'm not used to this, so be patient with me. All kinds of alarms going off in my house, so like I said, be patient with me. So, spring break, we were doing some probability exercises. So, I want to do a little bit of review, and then we're going to work through some basic problems. These will be problems like on the final exam. Okay, so first, some review. Remember that the probability of a simple event, that's an event that doesn't contain any other event as a component, is equal to the number of favorable outcomes divided by the number of total possible outcomes. The probability of some event A, our notation is going to be PR and then in parentheses A equals N. That just means that the probability of A is equal to some number N, and those numbers will range between 0 and 1. Mostly be fractions or decimal numbers. Now, if an event has a probability of 1, it must occur. An example of an event that has a probability of 1 would be getting either heads or tails on a single coin toss. You have to get one or the other. If an event has a probability of 0, it cannot occur. It's impossible to occur. So, for example, the probability of getting both heads and tails on a single coin toss, that just can't happen. So that would be 0. Complex probabilities. There are 3 kinds: negations, not sentences, conjunctions, and sentences, and disjunctions, or sentences. First are negations. The probability of not A is equal to 1 minus the probability of A. That's our first formula. Now, these formulas are in a handout on Canvas. You may want to print a copy of that off. For example, the probability of not getting a 6 on the roll of a single die. A die has 6 sides, remember, so the probability of getting a 6 is 1/6. So the probability of not getting a 6 is 1 minus that, which is equal to 5/6. Conjunctions. If you remember, there are 2 distinctions that we make. One between dependent and independent events, and the other between compatible and incompatible events. Well, for conjunctions, we're worried about whether they're dependent or independent. The definition of independent is that 2 events are independent if one happening or occurring has no effect on the probability of the other. Example would be getting heads on the first coin toss, then getting heads on the second coin toss. They are independent events. So the getting heads the first time isn't going to affect the probability of getting heads the second. So we'll see that in a second. If one event happening affects the probability of the other, then they're dependent. So here are independent conjunctions. If A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. If they're independent events, then the conjunction just multiplies the 2 simple probabilities together. The probability of getting all heads on 2 coin tosses is equal to 1/2 the probability of getting heads the first time times 1/2, same the second time. If we multiply those 2 together, we get 1/4. Dependent conjunctions. If A and B are dependent, then the probability of A and B is equal to the probability of B times the probability of B given A. So that little vertical line there, that means given that. So that's the probability of B happening given that A already happened. So the probability of drawing 2 kings without replacement, for example. If we have a without replacement problem, that means we draw out a card, and then we draw out the second card without putting the first card back. Now, that's obviously going to affect the probability of that second event happening because now we have fewer cards in the deck. So the probability of getting a king the first time is 1/13. 4 kings, 52 cards, that reduces to 1/13. times the probability of getting a king on the second draw, given that we already took a king out. Now there are 3 kings left in the deck and only 51 cards. So 1 over 13 times 3 over 51 is equal to 1 over 221. Compatible and incompatible events. 2 events are compatible if they can both occur. 2 events are incompatible if the occurrence of one makes the other impossible. Here are some examples. An incompatible disjunctions. If A and B are incompatible, then the probability of A or B is equal to the probability of A plus the probability of B. So if they're incompatible events, the disjunction is just the sum of the 2 simple probabilities. So the probability of getting either a heart or a spade on a single draw, that's equal to 1/4 plus 1/4, which is equal to 1/2. So there are 13 hearts out of the 52 cards. That's equal to 1, reduces to 1/4. Same for the spades. We add those 2 together, we get 1/2. And that makes sense, right? Because half of the cards are hearts or spades. The other half are clubs or diamonds. Compatible disjunctions. If A and B are compatible, then the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now, we worked out why that was the case right before spring break. Remember, it has something to do with counting the same thing twice. The probability of tossing heads at least once on 2 coin tosses. We have 1/2, it's getting heads the first time, plus 1/2, getting heads the second time. Now, we know the answer to this can't be 1 because that would mean we have to get at least 1 head. But we can get tails both times. So what we have to do is subtract the probability of getting heads twice, minus 1/2 times 1/2, since those are independent events. So that's equal to 1 minus 1/4 equals 3/4. Okay, so let's work some problems here. Say tossing 2 on a single toss of 1 die. So that's just a simple event. So we're going to toss the die once. One of those sides has a 2, so number of favorable outcomes would be 1, and the number of total possible outcomes is 6. So then the probability of 2 equals 1 over 6. Drawing the ace of spades on a single draw from a deck of cards. So again, that's a simple probability. We can say the probability of getting the ace of, now it'd be nice if I could draw a nice little spade there, but, well, that's not too bad. We'll leave it at that. Probability of drawing the ace of spades, a single draw from a deck of cards, equals one of those cards, only one is the ace of spades, 52 cards. Rolling a 12 with a single toss of a pair of dice. Now, this is easy to figure, but it is a complex event, so let's go ahead and work out the probability using the formula. The only way we can get a 12 is that we get a 6 on the first die and a 6 on the second die, right? So we have to get 2 6s to get a 12. Well, now we have to ask, are they dependent or independent, since this is a conjunction? And the answer is independent. What we get on the first die isn't going to affect the probability of getting anything on the second die. So that's equal to the probability of getting a 6 on the first one times the probability of getting a 6 on the second one. And that equals what? 1/6 times 1/6 equals 1 over 36. Okay, the probability of rolling a 13 with a single toss of a pair of dice. Well, you can't get a 13, so the probability of getting 13 equals 0. It's impossible. The highest you can get is 12. Tossing all heads on 3 tosses of a coin. So what's the probability of getting all heads? That's probability of heads on the first toss. Since it's all heads, that means and heads on the second toss and heads on the third toss equals, now we have to ask, are these dependent or independent? They're independent because what you get on the first toss won't affect the likelihood of anything on the second toss, and the same with the third toss. So that means the probability of those is equal to the probability of heads on the first toss times heads on the second toss times heads on the third toss equals 1/2 times 1/2 times 1/2 equals 1/8. Okay? Tossing heads at least once on 3 tosses of a coin. So now it's probability of heads on the first toss, or heads on the second toss, or heads on the third toss. Okay, what does that come out to be? Well, now we have to ask not whether they're dependent or independent, but are they compatible or incompatible? And in this case, they're compatible. We could get heads on the first toss and second toss and third toss all 3 times if we wanted, or any combination of 2 and tails on another. So what should we do? Well, anytime that you have compatible disjunctions, but you have more than 2 disjuncts, it's a lot easier just to use that negation formula. So what does it mean for that not to happen? Well, that means that we got tails all 3 times if that didn't occur. And that's easy to figure because that's the same as the getting all heads that we did before. So now it's what's the probability of not getting tails on the first toss, say, and tails on the second toss and tails on the third toss. That would be what that comes out to be, and we know that that is 1 minus the probability of getting all that, and the probability of getting all that is 1/8. So our answer to that problem is 7/8. Okay, may sound confusing, but it shouldn't be. So one way to think about these problems is that what's the probability of this happening? Is it high or is it low? So if we just think about, let me put this on here. If we just think about this here, is that probability going to be high or low? Well, we're very likely to get heads at least once, and that's what all that means. So that probability should be close to 1. Now, if it were the probability of getting heads all 3 times, we know that's unlikely to happen, so that's closer to 0. So now you work, once you think about that, whether it's going to be high or low, then you work through the problem, and if it comes out to be what you expect it to be, closer to 1, like this is down here, then that gives me some reassurance that I've done the problem correctly. Okay, what about drawing 2 red balls on 2 draws with replacement? Now, what I want to do is move this over a little bit. So now I put in the problem. Now, these problems are up on Canvas on a sheet, so with also the answer key. But over here, we've got a jar, it says, and it has 3 red balls in it. It's got 3 green balls, it's got 2 blue balls, and 2 yellow balls. So in a jar like that, what would be if you were to draw in your hand and get a ball out? It's a with replacement problem, so you check what color that ball is, then you put it back, and then you draw another ball and check that ball. So what would be the probability of getting 2 red balls in a situation like that? Well, we know that's the probability of, let me see this, Okay. Okay, that's the probability of getting red ball on the first draw and red ball on the second draw, and that equals what? Well, first question we ask, are they dependent or independent? And in this case, it's with replacement, so they are independent. So that's just equal to the probability of getting a red ball on the first draw times the probability of getting a red ball on the second draw. We just multiply them together. And our first one is, we've got 3 red balls, 10 balls total, 3 over 10, times, same thing for the second draw since we put that first ball back. And so this comes out to 9 over 100. All right. So no problems there. Okay, so let's try the next one. The probability of drawing 2 red balls on 2 draws without replacement. Okay, so this changes things a little bit. Now we have, since it's without replacement, they're dependent events. So that's the probability of getting a red ball on the first draw and red ball on the second draw. That is equal to, here's our formula for dependent events, probability of a red ball on the first one times probability of red ball on the second one, given that we got a red ball on the first one. Okay, so what is that equal to? Well, our first one, we've got 3 red balls, 10 balls in the jar, times, now here's our second. We've taken a red ball out, we assume, so now we've only got 2 left, and we only have 9 balls, right? So that comes out to 6 over 90, which reduces down to 2 over 30, which is 1 over 15, all right? If I'm making any mistakes, somebody let me know. Okay, drawing at least 1 red ball on 2 draws with replacement. So probably a couple of ways that we could do that. So the probability of getting red ball on the first one or red ball on the second one equals, okay, are these compatible or incompatible? Well, we've got more than 1 red ball in there, so we could get a red ball both times. So that comes out to probability of red ball on the first one plus probability of a red ball on the second one. Okay, but since it's compatible events, we have to subtract something, and that would be the probability of a red ball on both, which is that. Okay, now we have that, and we have to ask, are those dependent or independent? Well, it's with replacement, so they are independent events, which means we can just multiply those. So this is going to come out to be 3 over 10 plus 3 over 10 plus, or no, I'm sorry, subtract, right? 3 over 10 times 3 over 10. Okay, which is, this is 6 over 10. And then we subtract that 9 over 100. And if we have to make these denominators equal, so that's 60 over 100 minus 9 over 100 equals 51 over 100. Okay, I hope you're following along. Next, drawing at least 1 red ball on 2 draws without replacements. Let's see here. We have at least 1 red ball on 2 draws without replacement. Now, we can do this, definitely do this 2 different ways. We'll try one here. The probability of a red ball on the first one or red ball on the second one equals, okay, the probability of a red ball on the first draw plus probability of red ball on the second draw. Again, we have to subtract because we can get a red ball both times. So that's going to be the probability of both of them happening, getting a red ball both times. Okay, so now what does that come out to be? We've got 3 over 10 here, plus, not 3 over 10, but 2 over 9, right? No. Don't do that, okay? Follow the formula. It doesn't say given that. So 3 over 10 plus 3 over 10 minus 3 over 10. Now this one is going to have, because this is equal to the probability of red ball on the first one times the probability of red ball on the second given red ball on the first. So here is where we put 2 over 9. And that comes out to 6 over 10 minus, this is 6 over 90. So 6 over 90 reduces down to what? 6 over 90. That's 1 over 15. Is that right? 1 over, let's just keep that at 2 over 30 for now, because that's pretty easy to deal with. So this would be 18 over 30 minus 2 over 30 is 16 over 30, which comes out to be 8 over 15. Okay, questions there. Another way we could do it is to say, is to ask ourselves, okay, what would it mean to not get a red ball on 2 draws? That means that we got 2 non-red balls. Okay, so let me see if I can do it right. Well, let me see if I can erase something here. So that would be maybe, here we go. Give me a little room there. Okay. Here we go. So that means the probability of, whoops. Okay, probability of non-red on the first one and non-red on the second one. Okay, so how many non-red balls do we have? That's going to be, well, let's go ahead and make this explicit. Probability of non-red ball in the first one times probability of non-red ball on the second one given non-red ball on the first one. Okay, so that's going to be equal to 7 over 10. We have 3 red balls, so we know we have 7 non-red ones times, and we're not putting it back, so that means 6 over 9 there, right? And so what does that come out to be? That's 42 over 90, which is equal to, it's equal to 7 over 15, I believe. So, but we need to subtract that from 1, so 1 minus 7 over 15 is equal to 8 over 15, which is what we got the other way. So whichever is easier, you can do. Okay, drawing exactly 1 red ball on 3 draws with replacement. Okay, now if I remember right, this is a pain in the neck. So what would that mean? The probability of getting exactly 1 red ball. Now, what does that mean? Now I don't want to write this all out. It's really not easy or not difficult to figure, but it's a pain in the neck to think about. So what did it mean to get exactly one red ball? Well, here's one way that we can do it. We can get a red ball on the first one, right? And if we got a red ball the first time, to get exactly one red ball, that means we didn't get a red ball on the second one, and we didn't get a red ball on the third one, right? But that's only one way that we can do it. We can either get it that way, or we can get the non-red one on the first one and the red one on the second one. But if we do that, that means we have to get a non-red on a third one. And, of course, that's only one of the ways. We can get a non-red on the first one and non-red on the second one and red on the third. Okay, so to get exactly one red ball on 3 draws with replacement means we get either this or this or this. So it's a disjunction. You see, here's the disjunction, the or part, but it's a disjunction of a bunch of conjunctions. Okay, now the good news is that this probability is the same as this, right? And this probability is the same as this. So now about these ors, we have to ask, are they compatible or incompatible? Well, they have to be incompatible, because if we got this, that means we didn't get this, because this one the top one has a red ball on the first draw, but this one has a non-red ball on the first draw. So if we got the first one, that means we didn't get the second one, we didn't get the third one. All of them are incompatible. So if I can figure this up, then all I have to do is add that probability to this probability to that probability. But since they're all the same, all I really need to do is figure this one and multiply it times 3. Okay? So now we have to ask about this. Since it's a conjunction, are they dependent or independent? Well, it's with replacement, so they are independent events. I just need to multiply them. And here's what I'll do. The probability of getting a red ball on the first one is 3 over 10 times 7 over 10, probability of getting a non-red ball on the second draw, times 7 over 10. Okay, so this comes out to be 147 over 1,000. Okay, we multiply that times 3, and that gets us 441 over 1,000. Numbers get big, but it's really not that hard to figure out what to do. Okay, now here's one that seems complicated. What's the probability of drawing a red and a green, or a red and a blue, or a red and a yellow, or 2 greens, or 2 blues, or 2 yellows on 2 draws with replacement? Well, that's a lot to figure. Okay, it's a huge disjunction, and each one of those disjunctions is a conjunction, and it's going to be a mess to do. Now, but remember, right before spring break, I told you, if it seems like it's going to be really hard to figure something, then remember to ask yourself, what would it mean for that not to occur? Well, that includes every combination of a 2-ball draw except for 2 red balls. And we already know what's the probability of getting 2 red balls with replacement, because that was the first problem that we worked. And that was 9 over 100. So the probability of that not happening is 1 minus 9 over 100, which equals 91 over 100, which is just this probability of all of this stuff. Okay, that's the last one. Now on Canvas, I'm going to post that, and it's got the answer key, and the answer key is pretty explicit with all the math worked out. So I hope this works. I'm going to stop the recording now and try to post it, and we'll see.